Okay, so let me just share my screen. Yeah. So we are starting a new defense today. It's called control flow integrity, a discussion of a new defense. And let's see, the full screen. Okay. And this defense is called control flow integrity. So if you look at the schedule, I've actually dedicated 2 lectures for it. And the reason is because I don't think I'll be able to cover all what I want to today. We might spill over to the next lecture, but I will probably not take all of next lecture, in which case I will start and finish the next topic, which is state analysis, and based upon how I'm able to do it on Monday, the topic will be included for the midterm exam. I will let you know on Monday. Okay, but this particular topic of control flow integrity, it's a class of defenses against memory error attacks, and you will see that it takes a very foundational first principles approach to this problem. Pretty much like softbound, but the approach is going to be rather different in the way that it works. Okay, so the paper associated for this was from 2005, but the research into this continues, and I'll be able to explain what aspects of research into this continue to this day. But this is yet another paper, just like the return-oriented programming paper that won the Test of Time award 3 years ago. The reason you will see is that it gives you a very foundational feel in terms of the defense that it's proposing. All right, so it's a very clean formulation. So let me explain what control flow integrity is. I'll skip over this slide, which basically talks about the various forms of control flow integrity attacks. You've already seen them, buffer overflows, format string attacks, return-oriented programming, and so on. And then we will basically now talk about what control flow integrity is, or CFI. CFI is going to be control flow integrity for short. Okay, so the goal of this paper is to develop provably correct mechanisms, and I will explain all of these terms that are in red as we progress through the lecture to prevent powerful attackers. So we'll have to define our threat model carefully from succeeding by protecting against all control flow integrity attacks. Okay, so I will start with the last term first because that's the easiest to explain, right? So the goal of this paper is to protect against all control flow integrity attacks. What does that mean? So when we spoke about 2 lectures ago about things like return addresses, I used a particular term to explain what these are in a more general way, and I spoke about them as being control data, right? Because the return address and things like function pointers and so on, these are special data values that directly affect the control flow of the program. Okay, so they are called control data. And as we spoke about the first class, there are 3 goals for security: confidentiality, integrity, and availability. And in particular, we are going to focus on integrity. So what is integrity? Integrity basically means preserving the correctness of a particular value, right? Preventing an attacker from modifying the value in a malicious way. So this particular approach, CFI, takes the approach of trying to protect the integrity of control data values that are in the program's address space. Okay, so I will make that more precise, and as with any security mechanism, we will any security defense, we will have to understand both the mechanism as well as the policy, right? And we will split the lecture accordingly, right? So we will talk about what the mechanism here is and what the policy is. The goal of this paper primarily is to develop the mechanism for defense, which is the basic tools that allow this defense to work, while policy is left as an open-ended question. They provide some policies, but research into policy continues to this day. I will give you some examples of policies, but as you will see, providing a policy is a challenge to this day. Okay, Okay, so here is the key idea, and we will keep coming back to this idea over and over again. The idea behind control flow integrity is that during program execution, whenever a machine code instruction transfers control, it should target a valid destination. Okay, so as we know, from our study of machine code, there are various instructions that transfer control, right? Of course, if you talk about an instruction like add or push or pop, the transfer of control is implicit, right? Because after that instruction finishes, control transfers to the very next instruction. The more interesting instructions over here are instructions that transfer control non-locally or in a non-obvious way. So what are these instructions? Well, the call instruction, right? I mean, the call instruction, if you specify a target, you know exactly where you're going. But if you're calling something through a function pointer, for example, you do not know a priori, statically where the function will head to, right? So you need to know what the target of that call instruction is. Likewise, jump instructions or things like return instructions, right? You do not know where the control is going to return to. And what CFI essentially says is that when you transfer control, when a machine code instruction transfers control, you should target a valid destination. Now, this word valid is loaded because I have not yet defined it for you. And how you define this notion of valid is your security policy. Okay, but this paper says that all valid destinations are destinations as determined by the control flow graph of the program created ahead of time. Okay, so I will describe to you now. This is introducing a new term. So this sentence should clarify a few things for you. First of all, it works at the granularity of machine code. Okay, so you're not going to be concerned with source code here, although the examples that I will show you when I'm talking about control flow graph, call graph, and so on, concepts that I introduce will be at the level of source code. You should understand that all of the implementation works at the level of machine code. Okay, and this notion of valid or not valid is a matter of policy, which is how you define what is valid and what's not valid. And we will provide some candidate policies also that allow us to get a first cut implementation working. Okay, but we'll be more interested in the mechanism. Okay, all right. So now let me tell you what a control flow graph is, and this is a concept that comes from compilers. In fact, every compiler constructs a control flow graph of the program that it's trying to compile, and we have to understand what the control flow graph is. So I looked up Wikipedia. In general, I do not recommend just looking up Wikipedia for everything, but it's a pretty good description, so I thought I will use it. Okay. Rather than giving you a formal description, let me show you what a control flow graph is. You all have seen it in the past. Intuitively, you know what it is, but we'll have to formally define it. So what I'm showing you over here is the control flow graph of an if then else that basically shows you how control moves around in the program when you have an if then else statement. Likewise, here's a while loop, right? You have got some sort of a conditional, the body of the loop, and then based upon the conditional, you exit the loop or you continue within the loop. Okay. Do while is similar, right? You've got the conditional over here and the body is over here, and then you exit. Okay. So like this, you can draw control flow graphs. But what is a control flow graph? Right? I mean, if you have got a graph, you have to define what the nodes are and what the edges are. So let's take the simple program and then define the control flow graph for this program, right? If you've got a equal to 10, that's an assignment statement. Okay, so actually this should be a equal to 10 over not a equal to 0. Okay, so this program says if a equal to 10, then if a b is greater than c, a equal to b, else a equal to c. Okay, and then a print statement that follows the conditional. Okay, so you can see over here that this should be, as I said, a equal to 10. That's an assignment statement, following which you see this conditional compare, and then there is based upon b greater than c, you either do a equal to b or a equal to c. There's an end if, and then there is a node for the printf over here. Okay, so one way to think about the control flow graph is that every statement in the program or if you were to think about this in terms of machine code, every instruction is a node in this graph, and the edges basically tell you the control flow relationship, right? So if you have a conditional statement like this, which would correspond to a jump statement, for example, in the assembly, you determine what the two possible branch targets are, one for the true, one for the false, and you draw an edge between that instruction and the instruction that can potentially follow it. Okay, so it's important to remember that this is a static program concept, in the sense that you can define these control flow graphs ahead of time by just looking at the code of the program. And so, for this B greater than C, there are two possible targets, and so you draw an edge from this node to the corresponding nodes. Okay, so that is one simplistic way to define a control flow graph. But you will find that if you define a control flow graph in this way, then it is rather wasteful, because if you were to define one node for every instruction, then you will find that there are many instructions that just transfer control over to the next instruction, the very next instruction, and there is no way to go to any other node in the program. Okay, so you'll find long series of straight chains in this control flow graph that just pass control from that instruction to the very next instruction. So in the compiler community, they have defined this notion of what is called a basic block. So basic block is a sequence of instructions from which there is no exit except after the last instruction of the basic block. So the idea is that once you enter the basic block, you just have to go straight down, boom, 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 to the last instruction, and then at the last instruction, you have a choice of where to go. The other way to also think about basic blocks is that there is no branch target from anywhere else in the program's code that leads to the middle of the basic block. If you can ever call an instruction in the middle of the basic block as a branch target, you'll have to split your basic block over there into two basic blocks. Okay, so the nodes of our control flow graph are going to be basic blocks rather than individual program statements or program instructions. This lets us coalesce blocks that would otherwise simply be straight line chains in this graph, and the edges between the basic blocks represent the control transfer, the potential control transfer between the instructions in that program. Okay. All right. So the important thing to note about the control flow graph is that you can construct the control flow graph of a program in a very modular way, which is that you can now look at individual procedures and construct the control flow graph of each individual procedure and then compose them together. So, for example, if a function foo calls a function bar, you will just take the, okay, so before I go there, you can construct the control flow graph of each individual procedure separately. The only thing that you would do is that if there is a call of another function from that function, you will put a basic block saying call to the particular target. Okay, so if foo calls bar, you will have a basic block for call bar within that function, and you will just leave it over there as you're constructing the control flow graph for that procedure. Once you construct the control flow graph for all procedures, you will just compose them together by taking the call nodes in the corresponding control flow graph and then drawing an edge to the entry point of the procedure, taking an edge from the exit of that called procedure and then putting it back over here. Okay, so if you do that, you will get the control flow graph of the entire program. All right. Clear so far? Any questions about control flow graph? Any questions? Let's see. Okay. So there are no questions. Let's move on.
Sir, you said, sir, you said
sorry, yes, please go
that
ahead.
we can only make this. Hello, sir. Am I audible now?
Very faintly.
Sorry, sir, but
yeah, please go ahead.
So you can only make these graphs for static programs. So you cannot make if there are any dynamic return instructions or anything like that, you cannot make a control flow graph. Is that right?
You can, so you can make a control flow graph for any given program with the program as it sits on disk. Okay, so for example, if the program is going to dynamically link against a library, you can create the control flow graph for the program as well as the library. When the dynamic linking happens, you can also link together the control flow graph and create a more complete control flow graph as the library gets linked. Okay, so it's not like that. It's not like you cannot create the control flow graph of the program. You can create it, but it will have to be patched up at runtime. That's all.
So sometimes we don't know the return address or jump instructions address during compile time as it is calculated at runtime. So
okay, excellent point. Excellent point. Okay, so what you are saying, this is the point that I was just going to get to next, which is that, supposing you have a call through a function pointer or a jump through a register, you do not know the target ahead of time. Okay, so in which case, how do you construct the control flow graph? It's an excellent point. So this is sort of the forefront of the research, which is the granularity at which you can create these control flow graphs. So if you've got a jump statement or a call statement whose target is not known ahead of time, there are ways and means by which you can construct an over approximation. And the way you do it is using a program analysis technique called pointer analysis. I'm not going to get into details of pointer analysis here. I will mention it in brief. It is also there in the paper. For a full-fledged treatment of pointer analysis, you will have to take a course on compilers, such as the one that is being offered, I believe, right now by Professor Govindrajan and Uday, either this semester or next, I don't know when. But a pointer analysis is an analysis that goes over the code of the program and creates a superset of all the locations that a pointer can point to. So if you've got a call via a function pointer, that you can still create a control flow graph, a conservative control flow graph that over approximates the set of locations that this pointer can potentially go to. And that's the best you can do. You can show that it is not possible in a program, in a general program that contains, for example, loops and so on, to have a precise pointer analysis that gives you the exact set of pointers that the pointer will that the pointer can point to. That problem is actually undecidable. You can reduce it to so complete. A pointer in a particular location of the program can point to one of two locations, and you know that it can only point to one of two locations. But once you give an input to the program, that input to the program will tell you exactly which is the pointer, which is the destination of that pointer, and you cannot specialize the control flow graph at that time because that's a dynamic concept. Okay, so all of these things are coming up in the presentation, and you will see it. But that's an excellent point that you raised. How do you draw the control flow graph if you have pointers or unknowns? And the idea is that you will have to draw the control flow graph based upon a pointer analysis. Now for returns, I'm coming up for that. That's actually a very interesting discussion of its own. The way that you draw returns, for example, assume that this code over here, shown over here, is a procedure. What you would do is the following. Right? So if this is a procedure called foo and you call this foo from another location, you will draw an edge from here to every call location that foo can be called from. Okay, so there'll be an edge from here to every location that foo is called from, and that is how you deal with returns. It creates another problem, and that's coming up in a few slides. But hopefully this answered your question of how you draw edges in the control flow graph.
Yes, sir.
Okay, all right. Okay, so that's a control flow graph. Now let me talk about another related concept, that is that of a call graph. So a call graph is a graph that represents the calling relationship between functions. Okay, so in other words, if there is a function called main that calls another function called, let's say over here, add banana, you will be actually drawing an edge from main to add banana. Okay, and there's another one over here called eat bananas. Right. The point here is that, so you see over here, there are some numbers on these edges. We are not going to be concerned with the numbers over here, but the point is that main can call add banana 10 times. Okay, but there'll still be only one edge from main to add banana. Okay, main can call eat bananas just once, and so there'll still be only one edge. The important thing to remember here is that the call to eat bananas can actually happen conditionally. There can be an if then else statement inside main, and you can call eat bananas conditionally. Doesn't matter. you will still be drawing an edge from main to eat bananas, because that shows you that potentially you can call this function called eat bananas from this function called main. Okay, so that's the important thing to remember about this notion of call graph. If a function can call another function, then you will always have an edge from the calling function to the called function. This is called the caller and this is called the callee. Okay, the caller always calls the callee, main will call eat bananas, caller function, calling function. Okay, so now it should be sort of the algorithm should sort of spell itself out for you, which is that supposing I were to give you a method that goes and extracts control flow graphs from each individual procedure of the program, and I give you the call graph which tells you the calling relationship between various methods, you can actually construct a control flow graph for the entire program by looking up the call graph. How do you do it? Well, you look up the call graph and then you see which function calls which function, and then you patch up the entry and the exit edges of the control flow graph so as to get a complete control flow graph of the entire program, right? In the sense that you will at a node that is that's called that's a call node within this control flow graph, you will draw an edge to the entry point of the procedure, take an edge from the exit of the called procedure, and draw an edge back into the control flow graph of the calling function. So that's how you create a control flow graph of the entire program. Okay, so this, going back to the slides, when we talk about the control flow graph over here, we are talking about the control flow graph of the entire program, not an individual procedure. So what CFI says, or control flow integrity says, is that during program execution, whenever you have a control transfer instruction, it is going to target a valid destination as determined by the control flow graph. This is called the inter-procedural control flow graph, the control flow graph of the entire program created ahead of time. Okay, any questions? Okay. All right, so let's move forward. Okay. So we are going to consider a very, very powerful adversary, which is an adversary that can overwrite any data memory or registers at any given point in time. Okay, so it's a much more powerful threat model than softbound, where in softbound you did not have this threat model, right? I mean, in softbound you still assume that the only thing that you're protecting are buffer bounds. Of course, there's also the temporal protection, but you're only protecting spatial bounds of buffers. Okay, if you remember the format string attack, the format string attack worked by in order for the format string attack to work, we did not exploit any buffer overflows. We just went and used the %n construct to go and directly overwrite a memory location with the value chosen by the attacker. There were no buffer overflows that were exploited. So something like softbound, right? I mean, you'll have to ask yourself, is it effective over there, right? It's a very, very powerful tool, softbound, as well as the buffer bounds check. It's a very powerful approach, but you'll have to ask yourself, does it address the threat in its generality? And over here, right? I mean, we are considering an attacker who has got the ability to overwrite any data memory location of his or her choice with a value of their choice. Okay, but we will make some assumptions that you cannot directly modify the program counter, okay, and you cannot modify any sort of reserved registers, and this will become clear what these reserved registers are. All right, and we will also make an assumption that data memory is non-executable and code memory is non-writable. Okay, and we will see the need for these assumptions. So the way that I will develop CFI is that we will make certain assumptions and we will develop the core technique of CFI. Now on top of CFI, we will be implementing some applications that will allow us to go back and relax these assumptions of CFI. So for now, we will make a very reasonable assumption that data memory is non-executable and code memory is non-writable. How do you enforce this? Any suggestions or any thoughts on how we can enforce this?
Separating the pages.
Sorry?
Separating the pages. Separating the data pages and the code pages?
Yes, W XOR X, right? W XOR X is a simple solution to actually implement this, and assuming that our operating system gives us that ability, that will allow us to bootstrap application security on top of it. Okay, so we're going to assume that data memory is non-executable, code memory is non-writable. So this by itself will prevent code injection attacks, but we are not just interested in code injection attacks, right? Things like return-oriented programming are much more powerful than simple code injection attacks. So we're going to be able to prevent against that also. We can also prevent against things like format string attacks, and you will see that. All right, so I'm going to give you a slightly more detailed overview of control flow graphs than the simple overview I gave you, and this is kind of important. Okay, so one of the things that I will advise you is the following. After you read both the control flow integrity as well as a softbound paper, is for you to actually perform a side-by-side comparison of what attacks softbound can protect against and what attacks control flow integrity can protect against. I can tell you that they are not directly comparable. There are some attacks that softbound can protect against that control flow integrity cannot protect against. And there are some other attacks that softbound cannot protect against that control flow integrity can. Okay, so this will be an exercise that I leave for you as a reader, okay, or as a student in this class. And remember, this is just 2 papers, right? Softbound and control flow integrity. As the semester proceeds, we will see more papers, okay, and you'll have to compare all of them pairwise. And this, as an instructor, it's a very easy thing for me to sort of quiz you, because it gives me sort of n square possibilities to test you. But it's your job as a student in this course to do this homework. Whenever you read a paper, take all the papers that you've seen before and ask yourself, how does this current paper that I'm reading compare in power to the approaches that I've seen before? Okay, and this will help you get a much more thorough understanding of the paper itself. Okay, so that's one thing that I wanted to say. The second thing that I wanted to say is that unlike the prior papers that we have seen before, what we are going to see over here is a very clean separation between policy and mechanism. Okay, so I'm going to focus for now, when I'm talking about the control flow graph, about the policy aspects of this approach, of this defense, where we talk about what the control flow graph is, how we want to enforce it, and so on. And that is a point of debate, right? That's a point of where imprecisions can occur and so on, and where control flow integrity can potentially be defeated if you have a weak policy. But when I come to mechanism, it's going to be rock solid, in the sense that this mechanism over here, as long as you do the things that they're saying and follow their assumptions, there is nothing wrong with the mechanism of CFI. It's a rock solid approach. Okay, and if there are any weaknesses in CFI, they stem from policy. Okay, when I say rock solid, it's with respect to the assumptions. You can't expect CFI to solve all problems for you. So, for example, CFI cannot check buffer bounds, but it doesn't claim to check buffer bounds, right? The only thing that it claims is that at runtime, you give me a policy and I will enforce this policy. That's all it says. And at that task, the mechanism is able to perform its tasks only. So let's look at the notion of a control flow graph in slightly more detail than before. So, again over here, I'm going to start off with the definition of a basic block. And as I said, we will be looking at code examples, some pseudo code over here. It's not exactly assembly code, but you'll have to think at the granularity of assembly. Okay, so what's a basic block? A basic block is a sequence of instructions, a consecutive sequence of instructions or code such that the instruction in each position always executes those in later positions, and no outside instruction can execute between the 2 instructions in the sequence. Okay, simple way of putting it. So take this example. After this instruction executes, control automatically goes to the next one. That's one of the conditions, right? You should not have any other target after this x equal to y plus z and z equal to t plus I. Okay, so that condition is followed over here. But you can ask yourself, why have I drawn a separator between instruction 2 and 3? Instruction 2 is z equal to t plus I, and if you think about it, after z equal to t plus I, control will automatically go to the statement number 3. Okay, statement number 3 is x equal to y plus z. So why have I separated it? The reason I've separated it is because instruction number 3 is the target of a jump. Okay, so between instruction 2 and 3, you can potentially have other instructions that execute, which basically, you know, allows me to separate this basic block. So both of these conditions should be satisfied. The instruction in each position always executes before all of those instructions in later positions, and no outside instruction sequence can execute between two instructions in the sequence. Okay. So at this point, I have not used one of the terms in the slide, which is this notion of dominates. And I will actually ask you to go and look this up as homework. Okay, and I'm going to hold you accountable for this homework, which is the following. And this has nothing to do with you know, control flow graphs and so on. Given a graph, I want you to go and find out for me as a homework, what is a dominator and what is a post dominator. And I also want you to come up with the algorithms to find dominators. Okay, this is homework for you. When I say homework, it means that it is potentially testable. I might ask things in the exam that are related to this. So tell me, what is the notion? When do you say that one node dominates another node in the control, in a graph, in a directed graph? Okay, so find out the notion of dominator, and also go and do a search for the best algorithm to go and find dominators. And I will already tell you it's an algorithm due to Tarjan, who is the god of all things graphs. Okay, so there is a near linear time algorithm to find dominators. Of course, you know, that's the ideal algorithm. You should always try to think about an algorithm on your own. Try to come up with an algorithm that goes and finds dominators in graphs. Another related concept is that of post dominators. I also hold you accountable for your homework to find out for me what is a post dominator and the algorithm to find post dominators in a graph. Okay, but very loosely speaking, a domination relationship just means that, you know, it is going to appear this instruction. So this instruction 1 dominates instruction 2 if instruction 1 always appears in all paths from the start node that pass through to the exit node of the graph. Okay, so instruction 1 therefore dominates instruction 2 because it always appears in all paths that go from entry to exit and contain 2. They will also always contain 1 before. That's the loosely very speaking. That's the notion of a dominance relationship. Okay, but the notion of a basic block should hopefully be clear now. Both of these conditions should be satisfied. There should be no branch target that comes in the middle of a basic block. And once you enter the basic block, the only way to exit it is from the last instruction. Okay, as you can see over here, the only exit from 2 is to this basic block that starts with 3, but from 5 the exit actually goes back to 1. And this is an unconditional jump. You can also have conditional jumps where, you know, the target can go either here or here based upon the value of the jump. The jump can be conditional. Okay, it need not be an unconditional jump like this over here where control always goes back to 1. Okay, all right. So that's a basic block. Now a control flow graph is nothing but a graph where every vertex is a basic block and every edge is you draw an edge from a basic block Vi to a basic block Vj if there may be a transfer of control from block Vi to block Vj. Okay, there need not always be a control flow from Vi to Vj at runtime. Okay, it depends upon various things. For example, whether the conditional is true or whether, you know, branch whether the value of a particular pointer takes a particular value or something like that determined at runtime. But if there could ever be a transfer of control from block Vi to Vj, you draw an edge from Vi to Vj. Okay, all right. And as I was saying just a few minutes ago, the scope of a control flow graph is limited to an individual function or a procedure. Okay, that is called intra-procedural, which means that you take individual procedures and you construct control flow graphs. And if you want to extend it to an entire program, you have to have this notion of caller-callee relationship, which is provided by the call graph. Okay, so in a call graph, The nodes are not basic blocks, rather they are functions, function names, and there is an edge between two nodes in the call graph if a function vi can potentially call function vj. Okay, and you can see over here a simple example with three functions, orange, red, and green. Okay, so orange calls red two times with two different arguments. It also calls green. Green can potentially call itself and it can also call orange, and red does not call any functions. And you can see the corresponding call graph. Right, orange, there is an red, there is an edge to red, only one edge. We are not going to be treating this as a multi-graph. For our purposes, we will treat it as a graph, a regular graph with only a single edge between two nodes, and there is an edge to green because of this. And as you can see, green can call itself, and orange, so there is an edge from green back to orange. Okay. So clearly you can see over here that from the call graph it tells you various things, right? If the call graph has a cycle, it means that there is recursion in the program, right? And you can see recursion. Green is calling itself, green can call orange, orange can call green, so there's recursion. Okay, so you can also immediately look at a call graph, and if it's a directed acyclic graph, you know that there is no sort of recursive call relationship in the program. Okay. You can take any directed graph and if it has cycles, you can convert it into an equivalent that does not have cycles. The way you go about doing this is by identifying strongly connected components. Okay, if you were to find a strongly connected component and treat that as one big node, the resulting graph of strongly connected components will be acyclic. Okay, I will leave this as a homework for you to go and sort of look back at your algorithms textbook and prove this for yourself, right? If you have a directed graph that has cycles, the way to make it acyclic is to go and find strongly connected components in that graph, treat that entire strongly connected component as one giant node, and do that for every strongly connected component, and the resulting graph with strongly connected components as nodes and edges between them will be a directed acyclic graph. Okay, so you can always convert it that way. Okay, that's a general fact, nothing to do with this particular notion of call graphs. It is generic fact about graphs. All right, so that's your call graph, and now to construct your control flow graph for the entire program, or the inter-procedural control flow graph, which is also called the super graph, you just superimpose the CFGs of all procedures over the call graph. This is just what I told you, right? So what you do is that you take the control flow graph for red, you take the control flow graph for orange, and you connect them up in this way, where you put an edge from the call function for red over here, the call instruction for red, over to the entry point of red, and you take the exit from red, and then you connect it back to the instruction just following the call, and you do this at every location where red is called. Okay, if the call happens via a function pointer, you do a pointer analysis to identify the potential targets, and you draw an edge from the call instruction to every potential target that can potentially be called from there. And likewise, you draw the return from there back to the instruction just following the call. Okay. All right. So now I have to tell you about potential complication that's coming up. But any questions so far? About call graph, control flow graph, and how you compose them? Okay, let's move on. Okay. Now I'm going to introduce a concept. This concept is called context sensitivity. Okay, so this particular graph you will see after I explain it is a context sensitive graph, a context sensitive super graph, because the call return relationship is very clear. The sense that if I call from this edge, the return has to come back from this edge, and if I call from this edge, the return has to come back from this edge. Okay. So let me just go over and explain this notion of context sensitivity, and then come back to the slide of precision, and then sort of tell you what that is. Okay. So All right. So let us just take this example over here, right? Let's look at this slide. Ignore that red and green example. So supposing I've got a procedure over here. Okay, this thing I'm showing with my arrow is a procedure. It has two statements: A equal to ID of 4 and B equal to ID of 5. Okay, an ID is just a function that you implement. That's the identity function. Takes the argument, returns it back. Doesn't matter what that is. Okay. Now think about creating the control flow graph, the super graph for this program. Now I know that this procedure is calling ID, and over here I've got the control flow graph for ID, which is just one basic block, right? The entry and the exit. The question is, how do I link up the call sites back to the return site? Okay, so over here I told you one simple algorithm, right? You draw the edge over here and you draw an edge from the exit of this basic block back to the instruction, just following the ID. Same thing over here. You would draw the edge from here and then you return back over here. Notice that over here I have labeled the edges. Okay, this edge over here is labeled for this call and this return edge is labeled for this call. This edge over here is returned for this. This is returned for, and this is labeled with 5. Now supposing I don't do that labeling. Okay, if I don't do this labeling and I just draw the edges between this graph, I end up with something like this, where all the edges are in a sense labeled the same way, 4, 5, right? Doesn't matter. No label, right? I put an edge from this call and I'm putting an edge back over here to the return, putting an edge from here, putting an edge back over here. So what is the problem if I don't label the edges? So the problem that happens when I don't label the edges is that if I were to follow this graph, there is nothing here to indicate for me how I return from a call. So the following path, for example, would be a perfectly valid path. I come from the outside, I execute this ID function, I follow the call edge, and then I execute this function, and then I follow this return, and then I move forward. Okay, so I've completely skipped this ID 5 over here because all I did was I followed edges in the super graph, which just connected back call and return sites. So I went over here, I followed the basic block from ID, then I took one of the return edges and then come back, right? There was nothing to tell me that I should actually return back over here because I'm returning in response to this particular call over here. Okay, so if this way of putting just edges without labels, that just takes me over to this function and going back over here, which does not respect the calling context, is called context insensitive analysis, because I'm not keeping track of the context with which I came, and that's a potential problem. Okay, so whereas something where I label the edges, right, and if I call from 4, I can only return back from the edge labeled 4, is called a context sensitive analysis, because I'm keeping track of the fact that I entered this procedure with an edge called 4, therefore I must return only with the edge labeled 4. Okay, same thing over here. If I enter from an edge labeled 5, I cannot return from an edge labeled 4. I can only return from an edge labeled 5. That's called a context sensitive analysis. Okay, this actually has very deep connections to the theory of automata. If you go back to the theory of automata, you will remember that there are two kinds of state machines. In fact, there are three, right? I mean, there is finite automata and there is context. There is the notion of context-free grammars and push-down automata. Okay, so what is the principal difference between a finite automaton and a push-down automaton? Can anybody tell me? The stack, right? The fact that there is a stack gives the push-down automaton power to express certain languages that the finite automaton cannot express, right? And the reason is because if you don't have the stack, you don't have a memory of where you came from, and therefore you cannot express certain languages. And I will sort of let you go and do the homework or go and recollect what languages you can express with a push-down automaton that you cannot express with a finite automaton. Now, coming back to the topic that we are considering, if you were to consider a real-life example of program execution and control flow graph, and you were to think about the execution of the program in terms of its control flow graph, what can you tell me, right? Is that execution of a real program doesn't correspond? If you were to think about the execution of a real program, using its control flow graph and its super graph, can you tell me whether that particular graph, you can treat every graph as a finite state machine, right? I mean, every node of your graph is a state in the automaton, and the edges just correspond to transitions between the nodes in the automaton. Now, if I were to ask you to think about the execution of a program as an execution of the automaton, can you tell me whether a real program's execution corresponds to the execution of a finite state automaton or a push-down automaton? What is it? Which one do you think it is? Can I model the execution of a program as a transition through a finite state machine, a simple deterministic or a non-deterministic finite state machine, or should I think about it in terms of a push-down automaton?
Sir, push-down automata.
And why so?
Sir, because it is context aware. Any programming language.
Exactly, right? I mean, you have to at least keep track of this particular context of where you came from. And it's a very simple example, right? I showed you that you're entering over here from 4 and returning from 4. What if ID called another function? ID could call another function, and then you will have to keep track of exactly which edge you came from here, which is 4, and then ID might have called another function. But when you return to ID, you should return back from 4. So you should save this 4 somewhere. Where do you save it? You save it in the stack. That's what you do. And that sort of explains to you why you have a stack at runtime in a program's execution. And the return address is nothing but a way of representing this label. It tells you exactly where to return to, right? So the very fact that you have a stack in a program's execution tells you that if you were to model a real execution of a program, you're actually modeling it as a push-down automaton, okay? And the flaw that happened in this particular case over here is that by not labeling the edges, you're treating the supergraph of the program as a simple finite state machine, because there are no edges, there are no labels on the edges. The labels over here that you're seeing, this 4 and 5, they are the push and the pop edges of a push-down automaton. Whereas over here, by not labeling the edges, you're just treating it as a finite state automaton, and therefore you're treating the execution of what is a push-down automaton using a finite state machine. And you know that that's not possible. If you do that, there are going to be inaccuracies. That's exactly what the inaccuracy that leads to context-insensitive analysis is, right? You can enter through this edge and exit from this edge. Okay, so that's the connection to automata theory and program analysis. Okay, all right. So let's go back yeah. So let me just tell you. So supposing I were to give you this program over here, and I've drawn edges from ID to this entry point over here and return, and this is context insensitive. There's a very cheap way. I should not use the word cheap because it's not actually cheap. There's a very easy way to make something that is context insensitive. I can actually make it context sensitive. This graph over here. What do? Well, I create 2 replicas of this particular control flow graph of ID, have a replica 1 and a replica 2. And for the first replica, I draw the edge from here to here. And for the second replica, I use it to connect up. Automatically makes it context sensitive for me because I know that every call of ID every replica of ID is going to represent a unique call site. Okay, so that's a very easy, straightforward way of creating something that is a context sensitive graph and not having to label the edges. Okay, so I don't have to label the edges, and just without edge labels, I can get away and still have a context sensitive treatment of the entire super graph by having 2 replicas of ID, and the first replica will correspond to the first call, the second replica will correspond to the second call, and I will not have any such so-called false paths of the program. Right, this is a false path of the program. Enter from here, go over here, and come out through this edge. So I will no longer have false paths in that program because I'll enter through ID. I'll go to the first replica, and the first replica is the return. There will only be one edge back to the first ID, and there'll be the second replica will correspond to the second call. So I'll get context sensitivity for free by essentially creating 2 replicas. So that way of obtaining context sensitivity is called inlining because I'm just creating a separate version of this function for each call and essentially inlining it with every sort of instance where this function is called. Okay. Now I want you to take a moment to think and tell me whether inlining is always possible or whether there are any shortcomings of inlining. Can anybody think about any shortcomings of inlining? And more importantly, is it always possible to create an inline version of a control flow graph? Any thoughts? Okay, I will give you the answer now, of course. But in general, if I leave questions like this, I will not answer them, and those will be fair game as far as testing you is concerned, which is you're expected to do some homework. Okay, so there are two disadvantages of inlining. First of all, I will show you that inlining is impossible in some cases. Okay, and it's impossible if you have recursion. Okay, if you have recursion, you cannot create inlining. Okay, you cannot create a unique copy of the function for every unique call because the number of times that a function recurses is not known beforehand, right? So you cannot create a copy of the function for each unique call. So it's going to be impossible if you have recursion. But even if you didn't have recursion, inlining is not always a good idea because you'll have to create potentially an exponential number of copies of this function based upon the depth at which the function is called, exponential at the depth of the call graph. Okay, so in this particular case, I'll have to create two copies. But let's say ID has another function that it calls called foo. I will have to create 4 copies of foo if ID calls foo twice. Okay, and it keeps going. So if I have a call graph of depth n, I will potentially have to create exponential in n copies of a function at the leaf level, for example, to do inlining, to implement inlining. And what this means is that my call graph will get extremely large before I know it. And it will not even be amenable to analysis. I can't even load it in memory to do enforcement with things like CFI and so on. So it's in general not a very good idea, and you have a very cheap and succinct way of keeping context sensitivity, which is with this labeled edges. So why not going for that approach, which gives you context sensitivity? The only additional cost is that I will have to label these edges over here, which is that I'll have to keep track of where I came from and make sure that I only return to those locations. Okay, so going back, right? This notion of precision, this is a rather abstract notion. I'm not really going to hold you to it. The notion of precision of an analysis is often characterized by what are called soundness and completeness. Okay, so let me just briefly introduce you to it, although it is going to sound rather abstract now, but I will say it. Okay, so supposing that there is a universe of true things that somehow somebody tells me these are all the true facts about the program. Okay, and my analysis comes and returns a subset of those. Okay, so I've got some program and some oracle tells me these are all the true facts about the program. So what are these true facts? It could be, for example, the valid destinations of a pointer. It could be the valid call sites that a potential indirect call can target. Those are all the true facts about the program. Okay, and some oracle tells me these are the true facts about the program. Now I write an analysis to go and analyze the program and then spit out facts about the program. Okay, so the analysis tells me certain facts that are in this dark blue oval over here. If this dark blue oval is a subset of the true things, right? This true thing is given to me by an oracle. It's not given to me by any analysis. It's going to it's actually it goes and it sits within this true things box. Then I call my analysis sound, because I can be sure that the analysis never returns any untrue things. Whatever the analysis says is always correct, and if the analysis tells me that something is a fact about the program, I can believe the analysis, because the things I say, what the analysis says is a subset of the true things as given by an oracle. Okay, that's called a sound analysis. Of course, that's not good enough because I can miscorrect things about the program that the analysis will not say to me. Okay, so this will cause me, a sound analysis can cause me to reject facts about the program that are otherwise true. Now, the complement of that is what is called completeness, where if my analysis says a bunch of things, okay, all the true things that about the program are encompassed, but it can also say other things about the program that might not necessarily be true. And those are things over here where I'm pointing my mouse in this portion of the oval, where these are things that the program analysis says is true, but are not really true facts. Okay, so for those of you that are taking machine learning courses, you will see exactly the same concepts introduced to you using two other terms. They're called precision and recall. Okay, and I am actually going to leave it for you as a homework to go and tell me which is precision and which is recall. But this notion of soundness and completeness that comes in program analysis is also going to come to you in a machine learning course, because you see over there that it's exactly the same concept. There are certain true things that the universe tells you, and you have a machine learning, let's say a classifier, that tells you some things are true. Okay. Now, how do you characterize the performance of that classifier? You do so using precision and recall, and those concepts of precision and recall correspond exactly to this notion of soundness and completeness in program analysis. Okay, so ideally what you want is a sound and complete analysis that just, you know, a blue oval that goes and exactly covers this true things oval, but that's not possible because of the halting problem. Okay, in any real execution of the program, it is not possible to a priori design a program analysis that will give you exactly the true facts of the program and nothing else. You will have to compromise on soundness or completeness, and you can reduce this back to the halting problem. So you can never, just like you can never write an algorithm that tells you whether a program is going to halt on a given input, just like that, you know, sound and complete analysis is not always possible for various classes of analysis. So this is a known fact, and so we're going to have to live with it precision. Okay, so I gave you this notion of context sensitivity and so on. So let's now move on. Okay, so now let's go on to control flow integrity and the basic approach of control flow integrity, and look at the mechanism. Okay. All right. So the control flow integrity approach basically provides the following invariant, and it's always nice to think in terms of invariants because it provides a way to reason about the correctness of your approach. Okay. So supposing I give you a program, and I also write an analysis that goes and spits out a control flow graph. Now the control flow graph may not be precise in the sense that, you know, you might have a pointer analysis that tells you a whole bunch of targets for a particular pointer. Doesn't matter. You give me a control flow graph, and I will enforce for you at runtime that control flow graph is enforced. That is what CFI tells you. Okay. If you give me a control flow graph, you, the analyst, gives me a control flow graph, and I am the person who is designing control flow integrity or CFI, I will take that control flow graph as input and ensure for you at runtime that the control flow graph is adhered to by the program. Okay, if you give me garbage, you can expect attacks. So garbage in, garbage out. Okay, but if you give me a very, very clear, precise control flow graph that precisely represents the ground truth of the program, at runtime you are going to be protected because your control flow graph was a very precise version. Okay, so this is going to be our overall methodology. We are going to build the control flow graph statically. That is at compile time, you are going to try to create the control flow graph. I showed you how you can create the control flow graph. You're not going to be concerned with that so much now. Rather, I'm going to be now talking about the next few steps. Okay, if you give me a control flow graph, I'm going to show you how to enforce it, and the way I will enforce it is by instrumenting or rewriting the binary at install time. Okay, so I'm going to take a binary, analyze it statically, create a control flow graph, and then rewrite that binary so that at runtime, if you want to execute that binary, the control flow graph that you gave me, it will be enforced. Okay, there is going to be no other way of violating the control flow graph. So if you go and look back at things like code injection attacks or format string attacks. All of these are actually violations of the control flow graph. Okay, they are violations of the control flow graph. For example, in the simplest case, if you have a stack buffer overflow, you rewrote the return address and you return to another location that you did not intend to, that the program did not intend to return to. Okay, so it was a violation of the control flow graph. So if you give me a control flow graph that says that after foo I must go back to bar, I will enforce that for you. Okay. There are also a few other things, which is verify CFI instrumentation at load time and perform ID checks at runtime. These things will become clear as I explain the way that it works. And another thing that's going to be, I will not emphasize too much now, but I will come back to this, is that the whole mechanism is founded on the basis of having a small trusted computing base. Okay, it is incredibly complex to rewrite a binary and insert instrumentation. Okay, which means that the task of creating something that's going to rewrite a binary is as complex as creating a compiler itself. Okay, so now if you're going to rewrite a binary at runtime and expect it to enforce the control flow graph, does it mean that I have to trust everything that is rewriting the binary? Does it mean I have to trust the compiler also? Because the compiler, this is another giant piece of software containing a million lines or more. Do I have to trust that? In which case it becomes a recursive problem of having to, trust larger and larger pieces of software. And I will show you that that's not the case. Okay, you don't have to trust a binary rewriter. You just have to trust a small few hundred line verifier that just does a binary walk of the a linear walk over the binary and tells you if the binary has been instrumented correctly. Okay, so at this point I must emphasize another thing, and it must have become obvious from my description. The whole approach over here, CFI, works with binaries. It does not require access to source code. This is in contrast to the assumption that we made in softbound or fat pointers, where we did assume that source code was required. Okay, why did we make that assumption? Can you recollect? Of course, we implemented the compiler, but I also spoke about the fact that you don't strictly need the compiler. You can do it in binary if you want to, but there is a problem associated with it. What was the problem?
So for every integer, you have to assume that it
exactly,
can be a pointer.
Exactly. That's a very good point, right? So because any 4-byte value can potentially be a pointer, you have to potentially treat any 4-byte value, including integers, as pointers. And this exponentially increases the cost of the method. Okay, if you were to implement it that way. Required access to source code and the type system of the program. But what we will see now is that control flow integrity, this particular method works with binaries. That's a big selling point. Okay, but you will also see that the guarantees that it provides are not as strong as softbound in some cases. Okay. So what we will do now is that we will actually go and look at some code examples and see how to build a control flow graph. And I'm going to actually revisit some of these concepts that I spoke about, context insensitivity and so on. And it will become clear how we will resolve these issues. So for the purposes of what we are going to be doing now, let us look at this program on the left. And this is a real program that you can write with the utilities available on a typical Unix system. We have got a method over here called sort2, okay, that actually sorts two input arrays, A and B of a given length. And it actually calls the built-in sort method to do so. So if you have never used the sort method, I encourage you to do it. Actually, it's a Unix utility that's available as part of the standard C library that sorts arrays of simple types. Okay, but you are supposed to give it a comparator function. So the sort function takes 3 arguments. It takes the pointer to the beginning of the array, takes the length of the array, okay, and it also takes a comparator function. So over here, for the first sort, I'm giving it the comparator function LT, which is passed as a function pointer, as you can see. And the second one, I'm passing it the function called GD, or greater than. Okay, and LT and GT are simple implementations. LT simply returns the if x is less than y, it takes 2 arguments. If x is less than y, it returns true, otherwise it returns false. GT returns exactly vice versa. Okay, So what this does, as you can guess, is that sort2 sorts the first array in increasing order and the second array in decreasing order. Okay? Alright, so if you were to go and draw the control flow graph of sort2, what would it look like? Well, there is some code, it will call sort. Okay, we are drawing the control flow graph now over here using machine code. So call sort, I will draw an edge to the beginning of sort. Okay, and within sort, of course, I am not showing you the function body of sort, but you can imagine how it works. It takes a function pointer to either less than or greater than whatever is passed to it as the argument and calls that function. Okay, so while you can see call sort over here, because the call to sort is hard coded in the program, it is not entirely clear when I see a call in the sort function, what's the target of the call. It depends upon whatever is passed as the third argument of the sort function. So that's what is shown over here. It is a call via a register. So it can either call less than or it can call greater than. Okay, both are valid function targets. And why are they valid function targets? Because the sort is called with both the less than and the greater than in this program. Okay. All right. So those are the calls. And now, of course, I must also match the returns, right? Whenever I finish the sort function, I must return to the potential location where I was called from. Where was sort called from? Well, sort is potentially called from here or here. So the return can either go over here or it can go over here. That's what I've shown using this label 55. Okay, return can, so there is of course an address that you return to that's maintained in the call stack, but I'm just going to group together all the potential locations that this sort can return to using this label called 55. 55 is just a choice. I can call it 23. No, not 23. 23 is huge here. So I can call it, give me a number, 996. Okay, so I can take 996 and put it over here, here and here, but it's just telling me it's grouping together all the potential locations that this sort can return to, and I'm saying, look, I can return to one of these locations, which is either here or here. Okay, note that it's context insensitive. Okay, why is it context insensitive? Because it allows me, this particular control flow graph allows me to take this path. I can go from here, go over here, finish this return and return over here. Okay, that's wrong because I must be returning over here. And you will see that the very first iteration of control flow integrity that I'm going to present actually allows you to get called from here and return over here, or get called from here and return over here. Okay, all of that is possible because I'm lumping together all of the potential return locations of this return and grouping them together using this particular label 55. Okay, that's going to be allowed here with control flow integrity. So the control flow graph that I'm going to be giving you as input is just going to be a graph, doesn't have the push down labels, the stack labels, is just going to be a directed acyclic graph with no labels on the edges. Okay, so a call over here can actually return over here. That's going to be considered valid according to control flow integrity. Okay, but I will show you, and I will not have time to do it in today's lecture, but it will be in Monday's lecture, how you can take the simple notion of control flow integrity and use it to protect a second defense, which is a shadow stack or something very similar to a canary, where you maintain in the program's runtime space a stack of valid locations that you can return to and protect that stack using control flow integrity, so that whenever you return, you can actually check that you're returning to the corresponding call site. Okay, but the very first iteration that I'm going to present, and you will ask me, what good is this defense if I cannot even check that I'm returning to the location that I am, if I cannot even check that I'm returning to where I came from, what good is control flow integrity, right? Because that's the basic sort of attack that even simple stack smashing violated. What good is control flow integrity? But the way that we are going to build it is in layers, right? We are going to build the very first cut of control flow integrity that gives you the following defense, that it is going to assure for you already that the control flow graph is going to be followed. So for example, I can assure for you when you enter this sort using control flow integrity that the return from the sort is only going to this or this location. It cannot return to attacker injected code. It will either go here or it will go here. Now the attacker still has some flexibility, which is that once you enter this sort, you can instead of returning here, you can return here. But that's the only flexibility that the attacker will have. Okay, and we are going to further tie the hands of the attacker using other defenses that will be built on top of control flow integrity, which control flow integrity can provide strong assurances for. Okay, but even with basic control flow integrity, I can prevent arbitrary code injection attacks or even things like return-oriented programming kind of attacks where I return to arbitrary locations. Because by putting this label 55 over here, I've constrained this program's return to only go over here or here. I've not yet told you how. I'm just telling you what control flow integrity provides. It provides you the guarantee that once you come here, you can only return here or here. I'll tell you how shortly. All right, same thing over here, right? So this LT, it will only return to this location called label 23. That's what this red 23 says. That the return statement can only return to a program location that's labeled 23, and I will enforce this at runtime for you. So that will go there and that will go there. Okay. So what I want to warn you is that in the very first iteration, you will see context and sensitivity coming into play. That's still going to be okay because we have still tied the attacker's hands vastly. Instead of returning to arbitrary locations, I can only return to the pre-allocated locations as determined by the control flow graph. All right. Any questions so far? Okay, so the way that we are going to do this is by instrumenting the binary. Okay, so we are going to insert a unique number at each destination, and that is this 55, for example. And two destinations will be equivalent if the CFG contains edges to each from the same source. Okay, so if I have this return, I know this return can go over here or here. So both of these locations are going to be put in the same equivalence class and given the same label. In this particular case, that label is 55. Okay, so and what this thing over here, this call 17R is saying is that, look, this call instruction, it's an indirect call based on a register value, right? Whatever this register is populated with at runtime, this call instruction must transfer control to that location, right? So if this is a function pointer, this R can take an arbitrary function pointer's value and the call will simply transfer control to it. So what this call 17R is saying, and this is not a real instruction in x86 code, we will see how to implement this, but this is the effect I want. I want to be able to create these labeled instructions so that if I create a labeled instruction called ret55, that this ret55 will only return to an instruction where the label 55 instruction appears. Okay, ret55 will not succeed in any other way. Ret55, I want to create an artificial machine in some sense where I am able to create this instruction ret55 so that this ret55 will only return to instructions called label 55 and nothing else. Okay, if it ever returns to any other location, the program is going to throw an exception at runtime. That's the machine I want to create, and I'm going to show you how to create it. So this call 17R likewise is another instruction where if I have this register R, right, I'm going to check at runtime. I'm going to take this register R, I'm going to dereference it, go to that location and check whether the destination as specified by R actually contains this instruction called label 17. Okay, why label 17? That is what is specified as the first argument over here. Go to dereference whatever is provided by R, go to that location and check that the label over there is actually 17 that's matched to this call, and only then perform the call. If that label does not match, the call instruction will not succeed. Okay, that's the illusion I want to create. How do I implement this? That's what I'm going to tell you in the next slide. So that's this example of the instrumentation. Okay, so as you can see, right? Okay, so let's instead of a call, let's just imagine that instead of a call, what I have is a jump. I'm going to show you instrumentation one by one with the various kind of instructions. Okay, and I probably let me just go to the I'm probably going to stop at the slide. Without carrying any further, I'm going to let you go and read the paper. The next class, I'll actually come back and I will talk about some clarifying assumptions over here. Okay, so let us assume that we are given some binary code, and these are two instructions actually in the binary code. So this is the source. Okay, it says jump PCX. let us say that this ECX, what is the ECX? It's jump via register. Okay, so whatever the value this register contains, this jump instruction is going to treat it as an address and go over there. Okay, so let's assume that this is one of the potential computed destinations of this ECX. How do I know that this is the destination? Well, it's given for me in the control flow graph. I know that when I encounter this instruction, one of the edges goes to this location, and so this is one of the destinations. So let us just say that this destination instruction is over here. It's move EAX ESP. Okay, that's the destination. How do I enforce control flow integrity, or how do I provide the illusion that I was talking in the previous slide? Well, here is how. So at the source, what I will do is the following. Okay, so I'm going to insert these 4 instructions ahead of this jump ECX that do the following. I'm going to say move EAX 1, 2, 3, 4, 5, 6, 7, 7X, increment EAX. So what that does is that it creates the value 1, 2, 3, 4, 5, 6, 7, 8 inside this register EAX. And I'm going to say, look, take ECX plus 4 and compare it with EAX. Okay, that is, take whatever is ECX, that's going to be the jump destination, add 4 to it, and compare whatever value is over there with EAX. It should match 1, 2, 3, 4, 5, 6, 7, 8. Okay, what is this 1, 2, 3, 4, 5, 6, 7, 8? Is just one example. It's the ID. This particular case, the ID is 1, 2, 3, 4, 5, 6, 7, 8. But whatever ID you have, if it's 55, I would have loaded 54 over here, incremented it, and then obtained 55 in this register and check. Okay, I will actually tell you why I'm going to why instead of directly loading the ID over here, which is 55 or 1, 2, 3, 4, 5, 6, 7, 8, I'm loading the previous number. I will get to that next class. It's a small subtlety, but that's what I'm doing. Okay, and what I'm checking is that this is the conditional jump J and E. It says that if the value over here does not match, go to some exception handling code. That's what this error label is. But if it is successful, then only I go to ECX. So now I have to look at what I insert on the destination side. On the destination side, I'm inserting the actual label 1, 2, 3, 4, 5, 6, 7, 8. And what is this prefetch NTA? Well, what I want is the ability to have some sort of a no-op instruction. So this no-op instruction is just NOP, it does not have any arguments. Over here, prefetch instruction in x86 allows you to take a particular argument. So that's what I'm inserting. It's a harmless instruction. It does nothing. It just affects the state of the cache, but it's bringing forward this instruction. It allows me to specify the ID as an argument. That's what I put. Okay, so now let's look at the correct execution. Supposing no attacker has tampered with anything, ECX will contain the target over here. It will come move EAX 1, 2, 3, 4, 5, 6, 7, 7. That computes 1, 2, 3, 4, 5, 6, 7, 8 after this increment instruction. And then I go to ECX plus 4, which will be 4 bytes after this prefetch instruction. That's the target of the jump. Go here. It actually contains the 1, 2, 3, 4, 5, 6, 7, 8. That will be equal to this. And now I go to jump. Okay, so the jump will actually go now and jump to where? It will jump to this first instruction. It will execute the prefetch. Prefetch does nothing. It's almost like a no-op, and then start executing the target code. So that is how control flow integrity works. And if ever an attacker were to go and modify the value of ECX so that it points to some other location that is not in accordance with the control flow graph, the value at that particular location will not match ECX, and therefore you'll go to the error label. Okay, clear so far? Any questions? Actually, what's the time now? The time is 10 more minutes to class. So what I will do is, so this is a fairly complicated concept so far that I've introduced: the notion of control flow graph, the notion of call graph, the notion of context sensitivity, context insensitivity, and so on, and also this particular instrumentation. So what I will do is I will leave it at this today, and in the next class I will tell you, why did you actually compute the label? You should go and read the paper. There's the answer is over there, but I will give it to you in the next class. In fact, you should think about it before you read the paper. It will allow you to sort of understand better what the assumptions are. Okay, that's the first thing I will tell you. And the second thing I will tell you are, applications of CFI, how it enables more powerful applications, and how it lets you get rid of this context insensitivity and actually bring a context sensitive analysis to place. Okay, but I'll stop with this. Let me just stop the recording and then perhaps take any questions.